In the industrial heartland of North China, where roughly one-third of the nation's population powers its economic engine, a crisis has been building for decades. Rivers that once flowed year-round now run dry for months. Groundwater levels drop several meters each year. Instead of accepting this geographic reality, Chinese engineers set out to build the largest water transfer system ever attempted. 3 massive routes spanning 2,700 miles, designed to redirect entire river systems from the water-rich south to the parched north. But this unprecedented challenge means battling impossible terrain, pumping water uphill across hundreds of kilometers, and tunneling through earthquake zones. So how do you engineer 3 invisible rivers to reshape the hydrology of half a continent? Join man-made marvels as we explore the colossal project that proved humans could rewrite geography itself. The Eastern Route, the first of 3 massive corridors, begins where the Yangtze River meets the 2,500-year-old Grand Canal in Jiangsu province. From here, water must travel 718 miles north to Tianjin. 23 massive pumping stations were engineered to lift water across the route, each one a fortress of steel and concrete housing pumps, powerful enough to move entire rivers. The largest sits at Jiangdu. With an installed capacity of 454 megawatts, this single station moves 14,127 cubic feet of water every second, enough to fill an Olympic swimming pool in just 6 seconds, maintaining constant pressure across 718 miles of canal. But the physical challenge was only the beginning. The eastern route passes through China's most heavily industrialized corridor. When engineers first tested the water in 2008, they found something alarming. Contamination levels 8 times higher than safe drinking standards. Chemical pollutants from factories, agricultural runoff laden with pesticides, and urban sewage from millions of people had turned sections of the route toxic. The project faced a critical decision: abandon the eastern route entirely, or clean up 718 miles of China's most polluted waterways. They chose to fight. Hundreds of wastewater treatment plants were built along the route. Polluting factories were relocated, some that had operated for decades. Farmers were forced to adopt strict runoff controls. Over 36 critical monitoring checkpoints were established. If contamination is detected anywhere in the system, automated gates can isolate affected sections within minutes, the difference between a city's water supply and a public health crisis. In 2013, the moment of truth arrived. Engineers opened the valves gradually, watching pressure readings at each pumping station. The ancient Grand Canal sections, some over 1,000 years old, were tested under flows they were never designed to handle. For weeks, teams monitored every kilometer, checking for leaks, measuring water quality, waiting for something to fail. Today, the eastern route supplies 1/3 of Tianjin's drinking water, supporting a city of 16 million people in critical industrial zones. The route had conquered distance through mechanical force, lifting an entire river 213 feet skyward. But while the eastern route battled elevation through pumping power, the central route faced an even greater obstacle: solid rock. From the Danjiangkou reservoir in Hubei province to Beijing, water must travel 890 miles. But unlike the eastern route with its massive pumping stations, the central route would rely entirely on gravity. No pumps, no mechanical assistance, just water flowing downhill for nearly 930 miles. This meant the entire canal had to maintain a perfect gradient of exactly 0.02%, just 20 centimeters of drop per kilometer. Deviate by even a few centimeters over such distance, and the water would stop flowing entirely. But before any water could flow, the first massive challenge was the Danjiangkou Dam itself. Built in the 1950s, the original dam stood 531 feet tall. To store enough water for the central route, it needed to be raised to 579 feet, an increase of 48 feet. This wasn't simply adding height to a structure. This was surgery on a decades-old concrete giant while it remained operational. The problem is fundamental. As fresh concrete cures, it shrinks, creating stress at the interface between old and new concrete that could cause catastrophic cracks under water pressure. The solution came from California. The O'Shaughnessy Dam had pioneered a technique using step surfaces. By creating thousands of grooves in the existing concrete, they dramatically increased the bonding area between old and new layers. At Danjiangkou, explosives blasted the dam's surface, creating a massive stepped pattern. Steel rods were drilled deep into the structure, anchors that would tie the new concrete to the old. Only then could the additional 48 feet be poured. But raising the dam came at a human cost. The expanded reservoir would flood entire valleys. Over 330,000 people from Hubei and Henan provinces had to be relocated. Entire villages disappeared beneath the rising water. Families were separated. Children moved to different townships than their parents, breaking kinship networks that had sustained communities for centuries. Elderly farmers who had never left their villages were relocated hundreds of kilometers away to concrete apartment blocks in unfamiliar towns. Many never adapted to their new lives, mourning not just lost land, but lost identity. To prevent the dam from failing under the increased water pressure, a grout curtain was installed, a massive underground wall extending 213 feet beneath the dam's foundation. Thousands of holes were drilled and waterproof grout pumped deep into the earth, creating an invisible barrier that would hold the soil in place. With the reservoir secured, construction on the canal itself could begin. The Yellow River presented the most dramatic engineering challenge. Twin tunnels were carved 115 feet below the riverbed, each using a double lining system. The outer lining withstands external pressure from the soil and river weight above, while the inner lining handles internal water pressure. Between them, a drainage layer prevents pressure buildup that could crack either lining. Across the entire route, moving 28.9 billion cubic feet of earth required 5,000 excavators working simultaneously. Laser-guided systems ensured consistent slope angles, preventing stress points that could crack the concrete lining. The canal lining itself is a marvel of waterproofing. Concrete panels 4 to 5 inches thick, each measuring 16 feet by 10 feet, line the entire route. Expansion joints between panels are filled with hot bitumen sealant. In zones with unstable soil, engineers added an HDPE geomembrane layer beneath the concrete, a plastic barrier that prevents even molecular water seepage. In December 2014, the gates at Danjiangkou opened. Water began flowing north at precisely the calculated rate. Engineers monitored every mile, watching as the water maintained the perfect 0.02% gradient. 15 days later, it reached Beijing, 890 miles traveled entirely by gravity. The gradient had worked. The system had worked. Today, 1/3 of Beijing's drinking water comes from the central route, a lifeline for a city of 21 million people. The eastern and central routes proved the concept worked. But from the beginning, engineers knew these were the easier routes. The western route, the one Mao Zedong envisioned in 1952, remained on paper for a reason. It required engineering that didn't yet exist. The western route exists only on paper. The plan calls for diverting 600 billion cubic feet annually from the upper Yangtze tributaries on the Tibetan Plateau, often called Asia's third pole. The route must cross the Bayankala Mountains, tunneling through seismically active zones at 9,843 to 13,123 feet elevation. The proposed infrastructure includes over 186 miles of tunnels at depths exceeding 6,562 feet, deeper than any water conveyance tunnel ever built. In 2018, a test drilling crew at 12,467 feet abandoned the site after 3 workers collapsed from altitude sickness in a single day. The foreman's report was blunt: "We can't build this." The ecological concerns are staggering. Diverting 1/3 of the upper Yangtze's flow could devastate downstream ecosystems. The Tibetan Plateau's permafrost would be disrupted. Filling massive reservoirs in earthquake zones poses catastrophic risk. There's also a geopolitical dimension. The upper Yangtze tributaries feed transboundary rivers like the Brahmaputra and Mekong. India has raised concerns about potential upstream water manipulation. Critics argue the cost would exceed the eastern and central routes combined, and that desalination, wastewater recycling, and efficiency measures would deliver better returns. In May 2021, President Xi Jinping announced China would press ahead with the project. Preliminary consensus has been reached on a 141 billion cubic foot first phase. But the technical, environmental, and geopolitical hurdles remain formidable. Whether the Western route will ever be built depends on whether China can solve problems that have stalled the project for decades. The Western route's future remains uncertain, but that's not the real story here. The Eastern and Central routes have already delivered 2.68 trillion cubic feet of water to 185 million people. They've stabilized Beijing's groundwater. They've transformed northern China's economy. Yes, 330,000 people were displaced. Yes, 600 rivers disappeared. Yes, the Han River's flow was cut by a third. The cost was staggering, both human and environmental. But the engineering achievement is undeniable. China moved invisible rivers across half a continent, rewriting the geography that constrained a nation for millennia. The Western route remains unfinished, but here's the question for you. If you had to choose between engineering solutions and environmental protection, which would you prioritize? Drop your thoughts in the comments below.